Well, hi, everybody. In an earlier video, I talked about the four basic principles of counting, which were the addition principle, the multiplication principle, the subtraction principle, and the division principle. Now, those are four counting principles that are sort of underlying any type of counting of arrangements that we want to do. We can always imagine trying to use one or more of those four underlying principles. But at the same time, while we're solving a counting problem, while we're counting arrangements of objects, there are some other considerations that are very much at the forefront of what we're going to be doing. In particular, we need to know whether the objects that we are using to construct the arrangement that we're counting, whether those objects are allowed to be repeated, or whether those objects are not allowed to be repeated. And at the same time, we also have to keep track of whether the order in which the objects occur matters, or whether that order does not matter. So there are actually several combinations here as well that we have to consider, several possibilities depending on repetition and depending on order. And it would be helpful for us, I think, to look at each of those individually. However, as we're going to later see on the more complicated counting problems, it's often not as cut and dry as I'm trying to sound like it is. A lot of times order sort of matters. A lot of times repetition is sort of allowed. And you'll see what I mean by that when we actually look at some examples of it. But it's often not as cut and dry as just saying, yes, the order matters and repetition is not allowed. But we're going to, at least for the purposes of the easiest examples of counting problems that we have, specifically look at each sort of combination about order mattering and repetition being allowed. In this section, I'm going to talk about permutations of sets. And when I talk about that, what I mean here in terms of what I was just describing is that order matters and that repetition is not allowed. And when we are in this context, we are going to be talking about something called a permutation, and it's a permutation of a set. So let's write down a quick definition here that will sort of drive our conversation as we talk about this. Let's suppose that S is a set with n objects. And we're going to be using those objects to make arrangements that we would like to count. That's kind of the idea behind this. So I'm going to define something called an r-permutation. So an r-permutation of S is an ordered arrangement. So we're going to keep track of order here. It is an ordered arrangement of R objects from S. I'm imagining that everything in S is distinct. So we don't see in the set S, we generally don't count repeats. So if I had a set that had, X, Y, Y, Z, 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 Z in it as a set, this is really what I would call a set. This is sort of what we would generally refer to as a multi-set. And we can simply reduce this down and omit repeated occurrences of anything that we see. So the set S is really consisting of distinct objects only. And because the objects are all distinct and they're all distinguishable from one another, that's why we mean that repetition is not allowed, right? Because we can't have the same element more than once. Now, later, I'll start talking about permutations of multi-sets, where we have potentially the same objects repeatable, okay? But for right now, I don't want to look at sets that have repeats in them. And so I'm going to not allow repetition by sort of assuming that I don't have those repeats. Just as a quick example of this definition, let's suppose that my set S, let's just stick with a very simple setup for this. suppose that S has the 4 elements A, B, C, and D in it. Then the 2 permutations, so let's choose R equal to 2. The 2 permutations of S are, what's the definition again? This is ordered arrangements of 2 of these elements of S. So because they are ordered, I have to imagine, say, choosing A and then B is different from choosing B and then A. So when I write it out as an arrangement, I want to keep those distinct from one another. Okay. And then I, of course, do the same thing with A and C, C and A and D, D and A. Then we go to BC, CB, BD, DB, and finally CD and DC. Notice that we are not allowing any repeats here, so you don't see things like BB in the list. We're not repeating the B. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 possible 2 permutations of a 4-element set. This is what we have. So there are, let's make a note here, there are 12 of these. You can actually derive that number from the multiplication principle, because we can imagine constructing a 2 permutation as being 2 tasks. The first task being to choose the first letter, the second task, choose the second letter. I've got 4 choices for choosing the first letter. And then when I want to choose the second letter, because I'm not allowing repeats, the second letter has only 3 remaining possible choices. 4 times 3, that's the multiplication principle, and it gives me 12 possible arrangements. And I've actually written them all down here in this solution, okay? And in fact, you might even say that it would be better to write the answer as 4 times 3, because that really highlights the tasks that go into choosing a 2 permutation. And it emphasizes that multiplication principle even more clearly. Okay. Hopefully that makes some sense. Let's take a look at some other examples of permutations of sets. Let's ask the following example. This time I'm not going to enumerate all of the arrangements. I just want to count them. Often in combinatorics, that's all we're interested in. So how many 7-letter license plates? How many 7-letter license plates contain distinct characters? How many 7-letter license plates contain distinct characters? I'm assuming here that I'm using characters, in other words, letters only, and that would be 26 letters in the alphabet to choose from. And so I actually want to think of this as a multiplication principle again. I'm going to make 7 slots here. And that means I have 7 tasks that I'm going to do when I create one of these license plates. The tasks are to fill in the 7 slots. Now, in the first slot, I have 26 choices because I can put any letter in that slot that I want. But as I move to the second task, which is to now put the second letter into the license plate, I'm going to emphasize that I have to do distinct characters. So whatever character I put into the first slot, I can no longer use that same character again. I will only have 25 characters left for the second slot. And reasoning in the same way, every time I fill out a slot, I get one less way of filling out the next slot because I have to throw away letters that I've previously used in coming up with the answer. So this is actually can be expressed as 26 factorial divided by 19 factorial. It's also okay to write it this way. And here what I'm doing is I am just using the multiplication principle. Whenever we see slots like this, we're generally going to be using the multiplication principle to multiply the number of ways of filling out those slots. Again, the characters have to be distinct. That's why there's no repeats, in other words. That's why this is sort of a falling factorial number of choices. If we were allowing repeats and we could use the same letter everywhere, then we would literally stick with 26 choices for every slot, and we get a different answer. But here we have 26 choices, then 25, then 24, then 23, and on down the line from there. So we have no repeats. And at the same time, the order does matter, because if I write the characters of the license plate in a different order, it will be a different string. It will be a different license plate. So we are very much in the context of order matters, repetition is not allowed. It's a good example of that. Okay. There's a little bit of notation here that I want to spell out for you that we can sometimes use. We don't have to use this, but the number of R permutations of an n element set S. This will often be denoted. You'll even see this notation on a calculator button, P of n comma R. Permutations of an n element set that are R permutations. And so what is the formula for this? Well, you can see from the example that we are starting with n, and we are factorialing our way down until it's actually going to be n minus r plus 1. The number of factors that you see here in this expression, right? The number of factors that you see here is actually exactly r. There are r factors there, okay? In other words, this is actually n factorial divided by n minus r factorial. Okay, so in this example here, you see that n is 26, right? We have 26 letters in the alphabet. In other words, S is a set with 26 elements in it. And we are doing 7 permutations of that. In other words, here we have R is equal to 7. So the answer is 26 factorial divided by 26 minus 7 factorial. This is the answer here. Okay, let's take a look at another example. Practice this just a little bit more. I mentioned earlier that most problems in combinatorics are not just clear-cut permutations of sets, right? In other words, the issue of whether order matters and whether repetition is allowed is often not just cut and dry. There's usually some other constraints that sort of come into play. And here's maybe an example that we'll look at that I'm going to actually break it into parts so that we can do several parts here and see the differences. So 7 people. I guess we have to be really careful with combinatorics problems, right? It just says 7 people. We should assume that these are distinguishable people, okay? If for some reason we wanted to create a different problem, I could say something like 7 identical twins. In other words, where it looks like we can repeat the same person 7 different times because it's the same, they look the same. But here, I'm going to imagine 7 people that are all looking different. Let's say that there are 4 men and 3 women. 4 men and 3 women are to be arranged for a photo. We're going to arrange 4 men and 3 women for a photo. So here are some questions that we can now ask. How many first of all, part A, photos are possible. I also have to be very clear that I'm assuming that everybody is in the photo, okay? It's not that we're going to leave some people out. This is going to have 7 individuals in the picture. That should be really clearly stated, or at least it should be implied by the nature of the question, that these 7 people are all being arranged for the photo, not just some of the people. All 7 people will be in this photo. So I'm going to have 7 positions here. I'm going to draw slots again. The order matters, right? If all of the men stand on the left and all of the women stand on the right, that's not the same photo as if all of the women stand on the left and all of the men stand on the right. The order in which the people are arranged, we need to keep track of that. However, there's no repetition here because these are 7 different looking people. No person can stand in more than one place in this photograph. Right? There's really no constraints on the photograph here. We actually can put anybody in any position. They haven't told us that there's any restrictions. So we actually have 7 choices for which person stands at the far left. Then 6 people remaining to choose somebody in the second position. And then 5, and then 4, and then 3, and then 2, and then 1. And we just simply use the multiplication principle here. This is 7 factorial, right? And we can actually think of that as P of 7, 7 if we wanted to. Okay, so we have 7 individuals and we're looking at the 7 permutation, R is 7, right? So here, N equals R equals 7. And we can view that in the notation that I've got over here of P of N comma R, right? Great, so the answer is just n factorial in this case. Wonderful, so that's pretty straightforward. Now, what if I make a constraint here? Let's do another part where we have slight restrictions in place. How many photos show men and women alternating? Okay, so now we have a constraint. And as I'm looking at my 7 slots, I'll draw them again here. I have to be careful that the men and the women are alternating in those slots. Okay, guys, feel free to pause this video. Think about it for yourself for a second. How is the answer going to change? Common sense would dictate that the answer should get smaller now, because we're not just going carte blanche on any photo whatsoever. We have constraints now that the men and the women have to alternate. It should be fewer photos that satisfy this new condition now. In fact, because it's 4 men and 3 women, we can be pretty sure that so that we are able to successfully do the alternating pattern, that we have to start with a man on both ends and alternate from there with women and men alternating throughout the picture. So I've put M's and W's to stand for men and women in this picture. And so I have a sort of a factorial that I can do again, but this time, you know, for the men, I only have 4 men. So 4 times 3 times 2 times 1 to arrange just the men. And then staggered with that are the arrangements of the 3 women. And so we would get something like this. 4 times 3 times 3 times 2 times 2 times 1 times 1. This is literally 4 factorial times 3 factorial. It's 2 interlacing permutations. A 4 permutation of the 4 men and a 3 permutation of the 3 women. And there's 4 factorial and 3 factorial ways to do each of those separately. Okay. Let's try one more example. Let's suppose that we want to find out how many photos there are with the tallest and shortest persons, I guess. So the tallest person and the shortest person among the 7 people, right, stand next to each other. Let's suppose that they have to stand next to each other. So we can identify who these people are before we even set anybody up for the photo, yeah? And the way I want to think about this one is a little bit of a new idea, but I want to take that tallest and shortest person and actually glue them together to each other as if they are a block. So I'm going to quote unquote glue the tallest and shortest persons together, those two people together. And I'm going to use the multiplication principle to sort of set about these tasks. When I glue the tallest and the shortest person together, I actually have two ways to do that, because the tallest person could be on the left and the shortest person on the right, or the tallest person on the right and the shortest person on the left. Right? So there's two ways to actually do that gluing process in the first place. And in so doing, I create those two people into one block now, right? I've got the 5 other individuals that are not the tallest or the shortest, and then I've got this extra block. It is really just a 6th object now. And I now need to lay the 6 objects down into a 6 permutation, right? So then we arrange 6 objects. The 6 objects are the glued block that we've already talked about, plus the 5 other individuals that are not being glued at all. So we have 1 glued block, 5 individuals, that's 6 objects that we have to arrange. And the number of ways of doing that is just P of 6, 6. In other words, 6 factorial right here. Right. So my final answer comes from the multiplication principle. There's 2 ways to do the gluing, and then 6 factorial ways to now arrange everybody into the picture. So by the multiplication principle, we have 2 times 6 factorial ways to arrange this photo. In this case. Yeah. Feel free to pause if you need to, jot down any notes, any questions. I hope it's making good sense, but also good to think a little bit too. Okay. Let's do one more case. Call this part D. I would like to talk about photos with all the men standing consecutively. Okay. I want to imagine that all of the men have to go all together in a row. I'd like to talk about how many ways there are to do that. So maybe pause the video and think about it a little bit. We're going to use the same gluing idea that I just used on this last example. Okay. So part of the task of making this photograph is going to be to make sure that the men are all glued together to each other. If I do that, the question becomes, well, how many objects am I actually arranging? In the same spirit as the previous example, I have the 3 individual women plus 1 block. And this time the block is all 4 men, right? So we must arrange the 3 individual women and a single block of all of the men. That's actually 4 objects. That's actually 4 objects that we are now arranging. And there would be 4 factorial ways to do that. Right? Is that the final answer? In other words, I have woman number 1, woman number 2, woman number 3, and then a big giant M, which is a block of all of the men. Okay. So this is the setup of it. And so I can permute these 4 objects in 4 factorial ways. These are 4 distinguishable objects. Nothing can be repeated. Order does matter, right? Is there anything else I have to do, though? I have to remember that this big M here is actually 4 men. And I've got 4 men, which are M1, M2, M3, and M4, which I actually have to put into the block in some order. That's another task. And there's actually 4 factorial ways to do that task, yeah? Right? So there's going to be 4 factorial ways to glue the men into a block. So we sort of have 4 factorial showing up in 2 contexts. There's arranging the men within their block as 4 consecutive men. And then there's taking that block together with the 3 individual women and arranging that. And that's also 4 objects being arranged in 4 factorial ways. The answer here, again, by the multiplication principle, the answer is just 4 factorial times 4 factorial. Again, it's really good to leave the answer that way. Of course, this is really, if you multiply it out, you get 576. That's not as helpful as writing it as 4 factorial times 4 factorial with a little bit of an explanation of where those factors of 4 factorial have actually come from. Okay. Whew, take a breath. We've got several examples of arranging photographs here with a couple of twists in the problem. And those are the sorts of things we have to think through. Sometimes these tasks involve some subtle subtasks that we have to count very carefully. All right. Let's do one last example in this section on permutations of sets. And then I think we'll have a good foundation. We're seeing the factorials showing up a lot. That's very typical when there's no repetition and when order matters. You're going to see factorials all over the place. This example that I'm about to do is no exception to that. Let's take a look at it. How many 26 permutations of the alphabet? Okay, so we're taking the set, right? So S here is just the entire alphabet, A, B, C, D, and so on, all the way through Z. We're actually going to take all 26 letters and jumble them up into a permutation. And the question is, how many 26 permutations are, now if I just stop there and I say, how many 26 permutations are there of the alphabet? The answer would just be 26 factorial, right? 26 choices for which letter to put first, 25 choices for which letter to put second, 24 choices for which letter to put third, and so on. But I want to make this a little more interesting. How many of these 26 permutations contain the string cat and or bird? Okay. cat and or bird. Pause the video for a second. I want you to think about it. See if you can think through how many such 26 permutations there would be. Let me give you a little hint. I want to do that gluing trick again. The little trick that we learned on the photographs example. What are we going to glue here? Let's just talk about the 26 permutations that contain the word cat. Just cat. Don't worry about bird yet. Let's talk about cat. Can we not just glue the C, the A, and the T together into a single block? Of course, there's 23 other letters that are not even involved in the word cat. But let's just take the 23 other letters together with this one block that's just CAT all glued together into a single block. That's 24 objects that I'm now permuting in whatever way I want. 24 factorial. Okay. These are arrangements that have cat appearing within the permutation. Now, I'm doing the addition principle here because another possibility is that I would have strings with the word bird in them. And by doing the same gluing trick with the word bird, now I have 4 letters that are being used in the word bird. So I only end up with 23 objects to permute, which are the word bird and the other 22 individual letters of the alphabet. We would get 23 factorial permutations that include the word bird. Now, is that the final answer? What about strings that have both cat and bird in them? Strings like that have been counted here and here. There's really just one string, right? We shouldn't be counting anything twice. So if we have counted something twice, we had better subtract it out. We have over counted. We have double counted strings that have both cat and bird in them. I'm going to now subtract out however many of those there are. Well, you can see how to do that. I just glue cat together and bird together. So the 7 letters of cat and bird are being used up in 2 blocks. There's 19 other individual letters, right? Out of the 26 letters in the alphabet, I've got 7 of them tied up in the words cat and bird, and 19 individual letters. Well, 19 plus a block with cat and a block with bird is a total of 21 objects that I'm now permuting. So we have to realize that those strings were counted twice. And we should have only counted them once. So I'm going to subtract out 1 time the cat-bird combinations that are both present. This becomes the final answer. This idea of subtracting out duplications is something we're going to talk a lot more about and see many, many more examples of in the future. Essentially, we have to use something called inclusion exclusion. I'm not really referring to that formally right now, but seeing this idea of subtracting out duplications is a healthy thing to look at even at this stage because it does come up a lot. So, well, I hope that this has been a helpful example as well. Again, lots of factorials showing up because we have order matters, repetition is not allowed. One of the things we're going to have to be careful about, guys, is that as soon as order doesn't matter, or if repetition is allowed, particularly though when order does not matter, which we have not talked about yet, but when order does not matter, we really cannot draw slots like we were doing over here in some of these examples. The answers are not going to involve factorials so much. And we're not going to be talking about permutations anymore. So I have to be careful about getting too attached to the idea of drawing slots. Works great when order matters. There's a first slot, a second slot, a third slot, and so on. And we take care of those tasks and use the multiplication principle to count them. But in many arrangement type problems that we're going to see, the order actually does not matter. We can't talk about a first, second, and third slot. And so we have to be careful in terms of how we're thinking about it and visualizing it. Just a heads up, for the purposes of what we've just been talking about in this video, slots are wonderful. We get these beautiful factorial expressions showing up all the time. Relatively straightforward, but just be prepared that we are going to see some examples in the future going forward where it's not quite so accurate to be drawing slots to show what we're doing. Guys, thank you so much for your attention on this example and on these videos, this video that I've just shared with you about permutations of sets. There will be more to come, a lot more counting that we want to be doing, and I look forward to talking to you again in the near future about some of those other examples. But for now, hopefully this all makes good sense. Feel free to shoot questions my way. But I will let you go for now, and we'll see you again soon in the next video. Bye for now.